We want to gain skill at setting up Riemann sums to approximate integrals, and then taking limits and watching the Riemann sums magically morph into integrals. Is it really magic? It only feels that way. It is really rigorous math, but we're being kind of hand-wavy about it, partially for fun, partially for time's sake. And when I say for fun, I mean I'm serious. Partially for fun, it is. Now, when I was in your shoes, I was a math major, and I didn't like this hand-wavy math stuff because it wasn't rigorous, and I'm like, I wasn't sure if I was doing it right. And many of you will be in the same boat, especially in the not sure if you're doing it right part. Okay? And the answer to getting better is just practice, practice, practice. Reading, reading, reading. Listen to me, listen to me, listen to me. Think, think, think. All those things go into getting better at it. It's going to seem perhaps a little pointless with these examples because we can find the answers other ways. However, doing it in the way we're going to do it has benefits, pays dividends in the other sections of Chapter 8. We're going to gain skills to help us with harder problems. So the first problem to do what we're going to do here is number 8. I'm not going to show you the directions, but what the directions say to do is to take this picture and write an expression, first of all, for the area of this thin strip, it's called, in this isosceles triangle. Then use that expression to set up what's called a Riemann sum to approximate the area of the entire triangle. And then take a limit and let that Riemann sum become an integral. What do I mean when I say Riemann sum? It's just sort of a more general summation that could be thought of as representing a left-hand sum or a right-hand sum or a midpoint sum, any of those. And in fact, it could even be more general. You could take an arbitrary point in the subintervals to determine the heights of your rectangles. It doesn't have to be the left endpoint, right endpoint, or midpoint. It could be something arbitrary. We're not really worrying about it too much. So we just call it a Riemann sum in honor of a person named Riemann. So I'm just going to redraw this now on my paper. Section 8.1, number 8. Got this thin strip. I'm going to shade it. The height of the entire triangle is 5. The base of the triangle is 3. This distance right here is labeled h. And the width of this thin strip is labeled delta h. Now, in this context, well, remember that in math in general, when you see the capital Greek letter delta in front of a variable, we almost always mean change in. And this could be thought of as a change in height. However, it's probably more important to just think of it as a very small height. You want to think of delta h as being something very, very small, conceptually. First step is to write an expression for the area of that strip. Then adding up all such areas will give you the total area. And adding up means we're doing a Riemann sum, so in the end we do an integral. Since the strip is so thin, its height is very small, it's also going to have a small area. I'll call the area delta A. Now, it is a thin strip in this isosceles triangle. The sides of this thin strip are slanted. Here's where it gets really hand-wavy. Pretend they're not slanted. Pretend this is a rectangle. Actually, that's not too surprising. I mean, that's what we do with Riemann sums, is we approximate areas under curves with rectangles. So why not? delta A is approximately width times height. What is the width? I don't know. Let's call the width W for width. Width times height. That's the width. This is the height. Okay, here's a key thing I'm about to say to knowing what to do next. Whatever variable has the delta in front of it is going to be the variable in the end that you integrate with respect to. So h has the delta in front of it. We're ultimately going to do an integral with respect to h, not w. So what that means is I'm not done here. I need to rewrite this small area, delta A, in terms of h, just h and no w. I already have a delta h there, but I needed something involving h there. So what is it? Just h? No. Here's the trickiest part. I need to figure out how w depends on h. And it's not w equals h. These two quantities are not the same. They're related, but they're not the same. As h gets bigger, in fact, w gets smaller. W is a decreasing function of h. But what function of h? Oftentimes, you want to use some facts from geometry, and this is no exception. We want to use relationships between similar triangles. The entire big red triangle is an isosceles triangle that is similar to this smaller purple triangle. Similar meaning it's the same shape with the same angles, not the same side lengths, but the same angles. And the fact that those triangles are similar triangles, implies that I can set up an equality of two ratios, two fractions. Actually, there's more than one equality that can be set up, but I just need one of them. And I want this to involve both W and H. Focus on the small triangle first. Its width is W. What's its height? Its height, it's not 5, it's not H. What is it? 5 minus H, yeah. The length of the entire big triangle minus this distance here. W divided by 5 minus H is the ratio of this length, the base of the small purple triangle, to its height. That has to equal the corresponding ratio for the big red triangle. Its base is 3, its height is 5, 3/5. So W would be 3/5 times in parentheses 5 minus H, which if you distribute the 3/5 through becomes 3 minus 3/5 H. And that's what needs to go up here now. Now, a little point of possible confusion is that sometimes the book uses subscripts like H sub I, for example, and sometimes they don't. Do you have to? I don't think you have to. It doesn't look like any of the homework problems sort of label it that way. But in the reading, the first couple examples, they use subscript H sub I, kind of analogous to T sub I or X sub I for left and right hand sums, the endpoints of the intervals. Related to that is how you write your Riemann sum. The total area of the triangle is going to be the sum of these little areas I'm not going to bother with writing I goes from 1 to n here. The book does do that at first. In their first couple examples, they let I go from 1 to n. First 3 examples, actually. But then they stop doing that. You might say the authors are getting sloppy, but we're okay with being sloppy here. This is a situation not like proofs, where we do not want to be sloppy, where we're a little bit okay with being sloppy. Why? So we're just after the integral in the end and doing the integral. So we're just, all this stuff is just preamble to the integral. The delta A's are approximated by these things. And again, I could write I goes from 1 to n here, but we're sloppy. Okay, here's where the magic happens. Maybe even want to write magic happens. We want to let delta H go to 0 here. Effectively let n go to infinity. And like magic, the summation morphs into an integral sign. The 3 minus 3/5 h, well, that's kind of boring. It just stays as it is. And the delta h morphs into a dh. Magic. Well, be careful. We need to do a definite integral here. What is happening with h? H starts at 0 and goes up to 5. It's a definite integral from 0 to 5. Poof! There's your integral. Magic. And that's supposed to be the answer. Is it magic? No, it only feels that way. Are these things literally morphing? No, I only said that for fun. You can make this completely rigorous, but it's that's not nearly as much fun. It's more fun to just pretend it's morphing. But it does leave you with a sort of sinking feeling like, did I really do it right? Well, the proof is in the pudding in this case. We can actually find the answer. I mean, we know the answer has got to be 1/2 base times height is 7.5. That's got to be the answer. 3 times 5 is 15, divided by 2 is 7.5. We got to get an answer of 7.5 here, do we? Let's see. Oh, yes, I think we do. 7.5. Yay. So if you get the right answer, well, you either got super lucky or you were doing it right. Most likely you were doing it right. But again, is this worthwhile to do? I mean, we already know the answer. Is it worthwhile to do this? Yes, because this is practice with these skills that will help for harder situations where you can't really say just what the answer is. Including in the very next section, 8.2. What's going to happen? You're not going to be able to just look at it and say what the answer is. Let's end with one more example, this time with a volume instead of an area. It's going to be problem number 18. It's a cone. There's the picture. Now we're slicing the cone into thin hockey pucks, wafers, very thin, not strips anymore, but thin wafers or hockey puck shapes. Though they're not exactly, there's slanted sides there. They're not vertical, but we're going to pretend they're vertical for the sake of approximation and the Riemann sum. And then we just hope in the limit is delta y goes to 0. That what we've done is valid, and the integral that we get gives the right answer. And when I draw the, I mean, the slice here is separated from the other pieces just for the sake of visual clarity. It's not really separated in reality here. And probably if I'm drawing it here, I'm not going to draw it so it's separated. The diameter of the top, oh, we got units here, is 4 centimeters. Our final answer is going to be a volume, so it's got to have units of cubic centimeters. The entire cone has a height of 5 centimeters. For a given thin slice, this distance right here is labeled y, and this width right there, that thickness, is labeled delta y. Number 8, they used h. Number 18, they used y. Why? It's arbitrary. It doesn't matter. Could have used y in number 8 and could use h here. It doesn't matter. Just be consistent with what the book decides to do. But now we're trying to find the volume of the cone, not its area. It's a 3-dimensional object. So I should label this not delta A, but delta V for small volume. A thin hockey puck, a thin wafer, is a cylinder. Volume pi r squared times h, height. Pi r squared being the area of the bottom circle or the top circle. Pi r squared, what's the height? It's delta y. Remember what I said 10, 15 minutes ago? Whatever variable in your picture has the delta in front of it, that's going to be the variable that you integrate with respect to. Y in this case. I mean, that's the only variable in the picture. But I introduced a new variable I called r, the radius of this thing. But I've got to figure out how r depends on y if I'm going to do the integral in the end. 3-dimensional picture, seemingly no triangles. Until you imagine you looking at it more head on, sort of go down and look at it more straight on, then it looks like a 2-dimensional picture. And you can draw some triangles in here. The cone looking at it straight on looks like a triangle. This distance right there is the r. There's the y. You don't need to draw delta y in here. Focus on, say, these half triangles as being similar triangles. You've got this big one right there, and you've got a small one right here. They are similar to each other. Entire distance here is still 5 centimeters. The diameter was 4 centimeters before, so this distance right there is 2 centimeters, that radius. So once again, we have similar triangles. We're trying to figure out how r depends on y. I could do, for the small triangle there, I could do r divided by y, this distance right there where I'm pointing, divided by this distance, r divided by y. And for the bigger triangle, the corresponding ratio is this distance, 2 divided by 5, 2/5. So r is 2/5 times y. Substitute that back up here. R is 2/5 times y. Simplify. The total volume is the sum of the little volumes, which is approximately a sum like this. Now let delta y go to 0. in the limit as that happens, poof, the summation magically turns into an integral. The other magic thing here is that we get an actual equality, no more approximately equal to's. Summation times sign morphs into an integral. The function stays as it is, 4 pi over 25 times y squared. The delta y morphs into a dy. And I do need an actual limits of integration here. Y in this picture, like the previous example, goes from 0 to 5. Do the integral, 4 pi over, it'll be 75 y cubed. 5 cubed is 125. Can do some simplifying. This reduces to 25 and 15, and then we can reduce it more to 5 and 3. Looks like we got 20 pi over 3. Is it right? The formula for the volume of a cone is 1/3 pi r squared h. The radius of our original cone is 2, and its height is 5. This is 1/3 times pi times 2 squared times 5. 2 squared is 4 times 5 is 20. Yes, we got the same answer, 20 pi over 3. It checks. So what we're doing here isn't something you couldn't do some other way, but we're getting skills that will definitely help us on Wednesday as we do some problems in 8.2, where you can't really do it some other way. And after spring break, as we do more applications in section 8.3, 8.4, 8.5, probably skip 8.6 for time's sake. And this also applies to probability, these ideas, in a way I'll show you on Wednesday.